In this video, I want to talk about the three laws of logarithms that you see on your screen right now and how we can use them to expand and condense different expressions. So, first law here that we have up at the top, what I want you, the key points to notice about this would be that to begin with, we have a log base A of x times y. So we've kind of got two factors there. We have both the x and the y, two pieces that we're looking at, both under the same log. And what we've done on the right side is we have expanded that by giving each piece, the x and the y, both their own logarithms. Now obviously we can't just do that, so what you would want to notice has also changed is whereas on the left side it was x times y, we're now adding these two separate logs together. Okay? When you look at the second law, it is somewhat the same idea, except this time we're taking x divided by y. They are still under the same log though. And so then, what we did on the right side when we expanded, is we have now expanded so that we have, again, x with its own log and y with its own log. But this time, since we were dividing originally, we are now subtracting in between these two logs. So the multiplication changed to addition and the division changed to subtraction. Our third property is a little bit simpler than the other two were. This one, all you really need to notice is that you have an exponent on the x that we're taking the log of on the left side, and then on the right side that exponent has now become a coefficient in front of the entire log. Technically, we would still count that as expanding. I know that seems kind of weird to consider that expanding when we didn't really move too much, but if we want to be really strict, an exponent does take up less space than a coefficient does, so that n coefficient would technically take up more space than the exponent, making it expanding. Obviously, if we want to talk about condensing, then condensing would be going from the right side, where all of these are taking up more space, and condensing them into the left side versions that take up less space. So it just depends on which way you're asked to go, whether you're expanding or condensing as to which way you are going. Please do note that all I did there was explain how you're using these. This is not a video to explain why these laws work the way they do or anything like that. That'll be a separate video. All we're doing for this video is just explaining how to use them and showing you some examples of that. Also, the last thing I would add about these laws before we start doing some actual examples is do notice that the bases of the logs stay consistent. If it's log base A on the left side, every log that we bring in when we expand is also log base A. Same with every one of these. The base of the log does not change at any point throughout these laws. So for an example here, let's say we wanted to expand this expression that you see on your screen, log base 2 of 5x. So if I wanted to expand this, the idea is I want to give every single factor, each piece, their own logarithm. So instead of having both 5 and x be in the same log, if I'm expanding, I want to try and give both of them their own separate log. So if we look back at our logarithms, or really we should decide what operation is happening between 5 and x first, I suppose. So that'd be the first question to ask yourself, is what operation is happening between 5 and x? Well, that's multiplication. It's 5 times x. So if we look back at our three laws, we do have a law for when we are multiplying, right? When we have two things being multiplied together under the same log, we are able to split them up using addition. So that would mean the way we could split up this logarithm would be to change to where I have a log base 2 for both 5 and a log base 2 for x. And then all I need to do is make sure that my signs match up, and like the law said, if it's multiplication, then when we expand it, that should change to addition. And so that right there, that would simply be our expanded version of this logarithm. Now let's take a look at this example. Let's say I gave you log base 5 of x over 3. Again, looking to expand here. Well, if we wanted to expand, then that means I want to give both the x and the 3 their own log. So that's where I'd start with, is I'm going to write out a log base 5 of x as well as a log base 5 of 3, giving them each their own log. The question is just what the operation between them should be. And if we look back at our second log, we will see that when we have division, that ends up expanding and changing into subtraction. So this should be a minus in between these two logs. And that would be all you'd have to do to expand that expression. One more of these somewhat straightforward examples before we do a more intense one. If I give you log base 4 of z to the 7th, well, there really isn't any expanding to do as far as giving something else its own log. Z is the only thing that I'm taking the log of, so I can't put out more logs than I already have. The only thing I can do to expand this is the fact that I have a exponent that is taking up a little bit of space. When I do have that last property that says any exponent can be moved to the front as a coefficient of the log. And so that'd be all I could do here with this example, would be take 7, oops, sorry, I'm on the highlighter, would be to take 7 and move it to the front, so the expanded version would be 7 times the coefficient, or as a coefficient to be times log base 4 of z. That would really be all you could do for that one. Alright, let's put all of that together and look at a slightly more involved example where we're going to have to use multiple laws. In fact, we're going to use all the laws within the same problem. The goal still remains the same. I want to try and expand this expression as much as I can. So I'm looking for every different variable, every different piece that I'm taking the log of to get their own separate log, and I also want to make sure any exponents get to be written as coefficients as well. So I see everything here. I've got exponents, I've got division between different factors with the x being divided by the y and the z, and then I also see a y times a z down there in the denominator, so that's also multiplication. So we have everything. It's kind of up to you what you want to start with. Now you cannot start by putting the exponents in front as coefficients, because you wouldn't want to do that before you've split up to each individual log, because, like, for example, yes, at some point this 5 is going to go in front of the natural log, the ln, as a coefficient, but it's not for everything, it's just for the x log. So you wouldn't start with that. But as far as the first two laws, whether you want to deal with the multiplication or the division first, is entirely up to you. For me personally, I prefer to take care of division first whenever I can, just because writing fractions takes up more space than when you can write everything on the same level, same line, you know? So I'm going to start with the division. I know division changes to subtraction, so what I'm going to do is I'm going to write a natural log for the x to the 5th, giving it its own separate log, and then, using the subtraction expansion, I'm going to give a separate natural log for the y and third root of z. I'm obviously still not done because I have not yet split up y and z, but y and z were on the same level, the denominator of the fraction, so they would still be together since all I've done is split up with the division, expand using the division. Now my next step is, now that I've taken care of the division, now I can focus on this multiplication between the y and the z. Since that's multiplication, that would mean that I can split them up using addition, using the first law. So I would have the natural log of x to the 5th minus what I'm going to get from this, which would be a natural log of y plus a natural log of the third root of z. Now the catch here, and this is important, this is why I picked this example, is you have to recognize that while we did split apart the y and the z, this minus was already here, which means that subtraction, that minus, still has to go to everything that comes from that first natural log. So it doesn't matter how much splitting or expanding that I do here, everything that comes from this natural log right here, that subtraction needs to be going to it. So I am going to need to distribute that negative, making both of these negative natural logs. Meaning at this point, we are sitting with the natural log of x to the fifth minus the natural log of y and minus the natural log of the third root of z. Now, in all honesty, that really probably shouldn't be too surprising, because if you think about our original problem, we had both of these in the denominator. So if division is changing to subtraction in this expansion law, in these expansion laws that we're using, of course anything in the denominator should be negative, because that's the whole point of changing it to subtraction, right? So that's really how you can remember that rule if you want to. Anything in the denominator should be negative. Now, as far as finishing this out, we are supposed to take care of any exponents and move them to the front as coefficients. But before we do that, you need to recognize that we can represent any radical as an exponent. We've talked about this in earlier lessons, but any radical can be represented as a rational exponent, meaning a fraction for an exponent. So a third root of z could be rewritten as z to the 1/3. That's how I'd want you to think of this. Okay, I'd want you to think of this as we are sitting here with the natural log of x to the fifth minus the natural log of y minus the natural log of z to the 1/3. And so to finish this out, we could move our exponents to the front as coefficients of their respective logs, giving us a final answer of 5 times the natural log of x minus the natural log of y minus a now 1/3 times the natural log of z. And that would be your full expansion.